Yeah, they asked me to talk about Icy Moons surface and depth, and there was some other things behind. So what I will do is to speak mostly about Jupiter and Saturn systems. During the introduction, I just want to put the exploration of those worlds into the context. And very simple, we start with Jupiter. So around Jupiter, you have 4 Galilean satellites, Io, Europa, Ganymede, and Callisto. And I will speak mostly about Europa and Ganymede, for reasons I will tell later. And then for Saturn, I will speak mostly about Enceladus and Titan. Now, if you have questions about the others, I will be happy to answer, but these are the 4 main bodies I will speak about. Just to give you an idea, Enceladus is very small, 250 kilometers in radius, 500 kilometers in diameter. And Ganymede, which is the largest, if we don't count for Titan's atmosphere, so if we keep just the solid surface, Ganymede is about 2,600 kilometers in radius, so it's 5,000 kilometers in diameter. So it's a factor 10 between the smallest one, Enceladus, and the largest one, Ganymede and Titan. Okay, so what's the context? I think it was a couple weeks ago, there was a paper in EOS. So EOS is a journal from the American Geophysical Union. And they want to launch an initiative about interdisciplinary studies just to bring together the people to think about the emergence of life. And so thinking about the emergence of life, I just extracted this paragraph. Exactly when and how the planet's first organisms emerge onto the scene remain among the most elusive scientific questions. However, one key reality is well established. The earliest steps in life's emergence were interwoven with the evolving chemical and physical conditions of Earth's earliest environments. And when I see that, I remember what Darwin wrote in 1871. I don't remember who his letter was for, but he says something. But if we could conceive in some warm little pond with all sorts of ammonia and phosphoric salts, light, heat, electricity, etc., that a protein compound was chemically formed, ready to undergo still more complex changes. So this is what I call the little warm pond of Darwin. So this is one environment that we can think of for the emergence of life. And then the other one, which actually we started to think about at the end of last century, when geologists dive into on the terrestrial seafloor, they were looking at rocks, but they found life. But the life that we find on these hydrothermal vents on the terrestrial seafloor, this life is just evolution of surface life. So it's not life that emerged on the seafloor. It's just an evolution of life that we know. It's same DNA and things like this. At least I'm not a biologist. That's what I hear from my friends. So you have these 2 environments, and maybe we are all wrong, and there is a third one, or maybe there is a combination of those environments. But when you think of the emergence of life on Earth, then the question is there life elsewhere in the universe? And thinking about these 2 environments, you can make the parallel with Mars and the Icy Moons. So that's the context for the Icy Moons. I put on the left also the search for a planet that would be like Earth, and you already saw that in Quentin's talk, the distribution of exoplanets. So I won't speak at all about that. And of course, I won't speak about Mars, but I'm going to spend time about Icy Moons, because what we have discovered in the last 20, 30 years, actually now, is that under the ice crust of these moons, you have oceans. And in some cases, the ocean is in contact with a rock, and so you have conditions which are very similar to the conditions that exist on the terrestrial seafloor. Okay, so follow the water was kind of device mentor that people were looking for Mars, and the water has been found on these ocean worlds. And I like this cartoon from a paper by Coquel in 2016, where he defines an habitable world as having at least these 4 ingredients. So the water, then some elements, good physico-chemical conditions, and energy, which is, by the way, chemical energy. It's not the energy, internal energy from the planet. And also, it's possible that an environment is habitable, but is not habited, so it can be inhabited. So we will move forward. We will first start with the Galilean satellites, Europa and Ganymede, and then I will speak about the Cassini mission and the discoveries at Enceladus and Titan. Okay, Jovian system. That's a system you can observe with a very modest telescope. I have one in my garden. I mean, this is something I was able to see in January when there is no cloud in Nantes, which can happen. And you can see the 4 Galilean satellites. So you have Io. I don't know, because they are not. Europa must be here, Callisto is here, and Ganymede is here. But in the order, Io is the closest one to Jupiter. You have here the mass and the radius. Just to compare with the Earth has a mass of 6 times 10 to the 24th, so 100 times more than this. And you can see the various mass between Io, Europa, Ganymede, and Callisto. You have the periods, and so something which is important is that the three first satellites, Io, Europa, and Ganymede, are in resonance. So it takes about a week for Ganymede to go around Jupiter, 3.5 days for Europa, and 1.77 days for Io. And we were talking about exoplanets that go very fast around their stars, and actually the Jovian system is a good analog of this kind of system. So surface temperature is around 100 K, so it's a kind of equilibrium temperature. The density goes from 3,500 kilogram per cubic meters, so which is the density of rocks. So this is for Io, you can see that here. And you can have a density as low as 1800 for Callisto here. And you can see that Ganymede also has a density, global density, which is not very large, which means that you have a mixture of rocks and ice / water for these 2 moons. And on Europa, you also have a little bit of water, but much less than the others. So that's something also to keep in mind. There is much more water on Ganymede than there is on Europa, and this will have implications about the conditions, the deep conditions. So what do I forget? The young surface of Europa, we'll see that. The 2 types of terrains on Ganymede and the very old surface of Callisto. We know, so that's a kind of takeaway message, but I will show more details, that there is an induced magnetic field on Ganymede and Europa, and the interpretation of this induced magnetic field is the presence of salty ocean inside these 2 moons. For Callisto, the field is very weak, and so you have 2 interpretations. It could be also an ocean, a deep ocean, or it's due to the exosphere. Because Callisto is far from Jupiter, it has an exosphere, but the induced field is very, very small. Okay, so let's look at the Europa induced magnetic field. I think it was a major discovery of the Galileo mission. It was absolutely not expected. At that time, people were thinking that you had completely frozen Europa, so just ice on rocks. We didn't think that there could be an ocean, so that the ice crust would be decoupled from the rocky interior. So the reason why you can measure an induced magnetic field, so you can see here on this plot, the line, the thin line, is a Jovian magnetic field. And what is important is that the Jupiter's magnetic dipole axis is not aligned with the spin axis. So it means that when a satellite is orbiting around Jupiter, the magnetic field that he encounters varies during the period. And because you have variations of the magnetic field, then you can create an induced magnetic field if there is a conductor. So that's very important because I will say later, on Saturn, it's not the case. The dipolar field on the dipole on Saturn is aligned with the spin axis. So we cannot use magnetometers at Saturn in order to detect oceans on the satellites. And so what Galileo found is that the field, the measurement, is not following the Jovian magnetic field. And so you have an excess, a difference, and the difference is due to this induced magnetic field. From the amount that was measured here, you can determine the conductivity. Well, not really the conductivity. If you know the thickness of the ocean, then you can get the conductivity here. But there is a trade-off between conductivity and thickness of the ocean. But anyway, you have two values, boundary values for the conductivity in Siemens per meter. And here is just a plot of the conductivity of seawater for different salt concentration. So this gives an idea, and by the way, when you compare the amount of salt that you have in Europa's ocean with the Earth's ocean, because Europa's rock is much less than the Earth, it's quite a lot. So it means that there was a lot of leaching during the differentiation, and that there was a lot of conductivity, there was a lot of ions in the ocean. Okay, so discovery of this conductive ocean. Then we have another information from the satellite. It's called the moment of inertia. I won't describe too much, but I like to show just a few equations. So the mass is something simple. You know, you just integrate the different concentric shells from the surface to the interior, and you get the total mass of the planet. So we know the mass from the acceleration of the satellites. But actually, by having different orbits or flybys around the satellite, then you can determine the moment of inertia. So C is the moment of inertia relative to the spin axis. And you can see that the moment of inertia tells you the distance, or is sensitive to the distance of any mass inside the body to the spin axis. So X here you can consider it's a spin axis. So it's a kind of a degree 2. It's like someone who is skating. You know, if you put all your mass around your spin axis, you're going to speed up. If you put the arms far from your spin axis, you are going to slow down. So you have this kind of measurements, and it's easy to show that. So if you have more mass at the center, you will have a lower value, and it's easy to show that if the density is constant, then the ratio of the moment of inertia divided by the mass times the radius to the square is equal to 0.4, 2/5. And for Europa, it was measured at 0.346. So this is consistent with what we call a hydrosphere. So a hydrosphere would be everything with ice and water, overlying a rocky core, and it's even consistent with the presence of a small iron core in the center of Europa. The solution is non-unique, so you may have solutions where you don't need to have an iron core, but you have solutions with an iron core. And so this was a paper by Dave Stevenson back in 2000. in nature, where, having found the ocean, the temperature, he was thinking that in the rocky core, because we're looking at Io is very volcanic, so people were thinking, okay, it must be the same thing inside Europa, so we may have volcanoes also on Europa's core. And so if you have magmatism, as it is indicated here, then magmatism and water here, the water is in green in that case, then you can have some hydrothermal circulation. But I want to stress that we have no evidence of hydrothermal circulation at present time on Europa. What we have is just the presence of water, an interface between water and rocks, but that's it. Now, a little bit of controversy about the thickness of the crust. You have two ways to transfer heat, either by conduction. So in that case, you have the equation, it's very simple. The heat flux is proportional to the temperature gradient. Here I just put a straight line. It's not really a straight line because the thermal conductivity varies with temperature, so it's a little bit different, but it's enough to get an idea of how much heat can be transferred. So this is conduction. And if the thickness of the ice is large enough and the viscosity of the ice is small enough, then convection can start. So heat is transferred from the interior to the surface. So you can see here the plumes, the hot plumes forming at this interface. And in that case, the temperature gradient is linear in what we call the stagnant lead at the surface, subsurface here. And then the temperature is constant, almost constant. It's adiabatic, so it's not really constant, but it's only a few degrees in the ice. And so people started, this cartoon is from a more recent paper by Kalusova et al., but McKinnon did the same kind of calculation. Depending on the viscosity of the ice at its melting point, and we think from observation on Earth that it's between 10 to the 14th and 10 to the 16th Pascal second, you can be either in conduction or in convection. And the big difference is that the amount of heat you can transfer by conduction varies a lot with the thickness. You can see the thickness is at the denominator, so when the thickness increases, the amount of heat that you can extract decreases very quickly. So you can see you go from 50 milliwatt per square meters for 10 kilometers, and you have 10 milliwatt per square meters if you are at 60 kilometers. Now, if you have a viscosity which is less than 10 to the 15 Pascal second, 60 kilometers, you can extract between 20 and 30 milliwatt per square meters by convection. And you can see that convection is much less dependent on the thickness. So it makes a big difference, because if you have convection, then you could freeze out the ocean. If you can release enough heat from the interior, then you are going to freeze out the ocean. So there were two schools, and there are still actually two schools. People who think that on Europa we have just conduction and a very thin conductive layer, and people who think that we may have 20 to 25 or maybe 30 kilometers of ice. Now that we know that there is an ocean, the next question is how can we maintain an ocean if convection is so efficient to remove heat? We don't have much heat in the interior because if you think about radioactive heating, which is the main heating source for the Earth, for the rocks on Earth, there is not much heat on Europa, and the equivalent heat flux would be on the order of 5 milliwatt per square meters. So that would be on these sides here. Well, the answer is something we heard about. It's tidal dissipation. And we started looking at tidal dissipation. So I don't want you to remember, of course, these equations, but I just want to show that the amount of tidal dissipation that you have in a body depends on very small numbers of parameters. You have the radius of the moon. You have the frequency, so it's 2 pi divided by the period. And you can see that this this period is very important. So the closer the moon is from the planet, the larger you will have tidal dissipation. You have a power of 5 here. And then you have the eccentricity, but finally the eccentricity is to the square. Of course, if you don't have any eccentricity, then it goes to 0. The thing is that if you have only one satellite with an eccentricity, what's going to happen is that the dissipation is going to circularize the orbit, and the eccentricity will go to 0, and then there is no more tidal dissipation. So when you do the calculations, you have to take into account the evolution of the orbital characteristics. At the same time, you are computing the interior temperature and the amount of dissipation. Oh, by the way, I forgot to mention there is a number here, which is the log number K2, and it's an imaginary part of K2, and this number tells you how the body is going to deform as it orbits around Jupiter. Because it has an eccentricity, the distance to Jupiter varies during the orbit. It can be described by what we call a potential. And then you have an equation between that connect the potential, the body forces, which is just the gradient of the potential, to the deformation of the body. And so you can do the calculation. The real part would be the elastic deformation. The imaginary part would be the viscous dissipation. Sorry, I say the elastic, no, sorry, the elastic deformation, and the imaginary part would be the viscous deformation, and so the viscous dissipation. What is nice is that we have observations of Io. We know all the parameters for Io except this one. So actually for Io, we can determine the imaginary part of the K2 number. So we have an idea of how Io responses to its orbit around Jupiter. By the way, we know that because we know how much heat flux is coming out of Io. Yeah, I put also here the definition of the quality factor because it's something you can hear about for the moon, the Earth, the moon, for other bodies, for exoplanets. And the quality factor is a ratio between this log number, which is the total, somehow the total deformation, and the imaginary part. And typically can be values up to 100. Now the question which is important is how is distributed tidal heating? Is it mostly in the ice or is it in the rocky core? Because this equation gives you the total heat which comes out of the body. It doesn't tell you where the heat is deposited. And so there is debates about how much heat, and this will depend on the temperature, so the viscosity of the ice, and the same for the rock. So recently there was a paper by Marie Beunkova and co-authors. It was in 2021. And so they predicted that inside Europa's core, you can have places where you have partial melt. And then the next question is whether the magma can migrate to the interface between the rock and the ocean, and whether you can generate hydrothermal circulation into this environment. So it's not impossible. Models can predict that. Other models would predict that most of the heat is actually in the ice crust rather than the rocky mantle. What they show also, which I think is important, is that when the orbital characteristics change because of this Laplace resonance between Ganymede, Europa and Io, then you have a pulse of heat which can generate magma inside the body here. What about composition and tectonics on Europa? So we don't have a lot of information about composition from the Galileo spacecraft, unfortunately here. But we do see that there are places which are very actively tectonized, and these places have a non-H2O molecule, and there is still debate whether it's sulfuric acid or sulfates. It has not been solved. So people who work on the possibility for life in Europa's ocean, they are interested in chemical energy. We know that because of Jupiter's activity, you have oxidants that can arrive on the surface. And then, so they model three different kinds of ocean. You have the oxidized ocean, where you can see a lot of oxygen, of course, in the molecules. You have the reduced ocean. So, for example, you will find some methane, NH4+, CO2 in the ocean. And then you have what they call the biological ocean, where you have a transfer between the surface and the interior. So you have oxidants and reductants here, and the same at this interface between the ocean and the rock. So determining the composition of the ocean can be important. Determining what kind of molecules are present in the ocean would be really important. And so the idea is whether these molecules can make it to the surface, and other places on Europa where we can see those molecules. There was some excitement when Hubble observed hydrogen and oxygen in ultraviolet glow at 200 kilometers above Europa. And by comparing that with what I will tell you about Enceladus, where you have real geysers that have been imaged by Cassini, people were thinking that maybe we have water ice plumes. I have some doubt because the physics is different between Europa and Enceladus, just because the pressure is quite different, the gravity is very different, but anyway, it's interesting. It's not yet confirmed. There have been other observations, but there is no correlation between those observations and the orbital characteristics of Europa. So we don't know. It's definitely something different from Enceladus. If confirmed, the plumes would imply that Europa is active, and maybe that the interior water is coming to us. So future missions could analyze these plumes. But again, this is only a few observations, and people are very cautious. Just to give you an idea, the same kind of observations were made at CNRS before the down mission arrived at CNRS, and it has not been confirmed by the down mission. So we have to be careful about this interpretation. Tectonics. You have a lot of faults on the surface of Europa. When we got this kind of image, actually you can play with that. It's like a puzzle. You can put the different plates back together. So it shows that there must have been some displacement of the surface of Europa. We find a lot of extension features. We have very few compression features. You can see here some kind of cryovolcanic area where you see it's very smooth on this area. It covers some of the faults that existed before. Again, very few impact craters, so it's pretty young surface on Europa. And so there is one paper with Louis Proctor as co-author, I forgot to put the reference, where they suggest that this long lineaments that they find on Europa, this thing here, could be related to some kind of underplating on Europa. People are interested in kind of subduction or underplating in order to transfer some of the oxidants from the surface into the ocean. But because ice is much lighter than water, actually it doesn't work like subduction zones on Earth. And for Europa, let's go to Ganymede. Actually, I don't remember when I started, but that's okay. Yeah. Largest moon in the solar system, two types of terrains. You have these bright terrains, which are less heavily cratered, but still more cratered than Europa's terrains. And then you have these dark terrains, which are very heavily cratered. You have this dipolar magnetic field I'm going to talk about. So not only on Ganymede you have an induced magnetic field, but you have also a dipolar magnetic field. So the induced magnetic field for the deep ocean, and Ganymede is going to be the target of the European Space Agency JUICE mission, which will be launched now in 2023. It has been postponed by 6 months or a year because of the sanitary situation. Okay, some surface features. There is also some tectonics on Ganymede. I remember that when we got the first images from Voyager, people were thinking about also plate tectonics on Ganymede with groove terrains that you can see here, what they call palimpsest, which seems to be an impact crater which has been eroded, or that was very, very old, or maybe just went into the ice crust and created some kind of different composition. You have the multi-ring patterns that you have here. You see the center of the impact crater, which is here, and maybe some kind of cryovolcanic area which are represented here. I just put the scale bars to give you an idea of the size of these features. But that was another discovery of the Galileo mission, completely unexpected. People were not thinking that you can have inside an icy moon liquid iron. So it means temperature on the order of 1500 Kelvin in the center of Ganymede, and it was not predicted by any model before we had the observations by Galileo. And this magnetic field is pretty strong. You have something like 350 nanotesla at the surface of Ganymede, or a few hundred kilometers above the surface. And it has been confirmed. I mean, we had 5 flybys of Ganymede, and every time we were able to observe this magnetic field. And so the modeling actually of this magnetic field is a challenge. For people modeling the Earth's dynamo, if they have a model, it has also to explain Ganymede's magnetic field, Ganymede's dynamo. So it's kind of end member in terms of the intensity of the magnetic field. I just put here what we call the magnetic moment, which is 2 orders of magnitude, more than 2 orders of magnitude smaller than what we have for the Earth. Interior structure, major difference between Europa and Ganymede. I told you Ganymede's density is smaller than Europa's density, more hydrosphere, the fraction of hydrosphere is more important. And now let me introduce the phase diagram of water. Water is very interesting. I can see people drinking water. Yeah, it's good. No, go ahead. But if you think about a solid, you have a liquid and a solid. You expect the solid to be denser than the liquid. Why a solid should be lighter than the liquid? I mean, apparently the atoms are closer to each other. So ice is, I think there are only 2 molecules for which the solid is lighter than the liquid. And the reason is that the ice crystal, when you look at the ice, it's full of emptiness. I mean, you can put a second network of ice inside the network of ice. So ice is very light. So that's why you have this the melting temperature of ice, which decreases with pressure. That's the vertical axis is pressure, depth. That's why I put it this way. Horizontal axis is temperature, 273 at 0 pressure. And then the melting temperature is decreasing because the solid is less dense than the liquid. But at some pressure, then you change the crystalline structure of the ice, and you have what we call the high pressure ices, and high pressure ices are denser than the liquid. And so what happens in terms of the thermal profile is that you have the temperature in the crust, which is going to reach at some point the melting temperature of the ice. Then you have adiabatic transfer of heat. Here it's almost constant temperature. And at some point, you are going to cross the freezing point of high pressure ice. And so the water on Ganymede is sandwiched in between the low pressure ice, the ice we know, and the high pressure ice. And what is important is that you don't have a contact between the liquid water and the rock. So the interior structure of Ganymede, iron core, very hot, silicate mantle, high pressure ice, ocean, surface ice. We don't know the thickness of the surface ice, the outer layer. We don't know the thickness of the ocean. A model or problem that I wanted to tackle when I started working on Ganymede, I think my first paper was back in 1982 or something like this on Ganymede. Was on high pressure ice, by the way. And I wanted to know how you can transfer heat from the interior to the ocean. And actually it's a complex problem because you are very close to the melting point, and so it's a two-phase problem. You have to take into account liquid and solid when you do this kind of problem. And so we did that more recently. This is a study by Kalusova et al. In 2018. Here the dashed line is a melting point of high pressure ice. So you have liquid on the right and you have solid on the left. The colors are the temperature difference between the temperature profile and the melting temperature. So what is blue doesn't mean cold, it just means that it's far from the melting temperature. And what you see is that at the interface with the ocean, you have what we call a temperate layer, which is a kind of mush, a mixture of liquid and solid. And at the interface with the rocks, actually that's what I wanted to look at, is for which conditions you can reach the melting temperature of ice, so get some water at this interface. And so we found out what were the parameters, the viscosity, the thickness, things like this. But what is important is that you cannot have a lot of water present at this interface. Actually, the amount of water that you can have is driven by the porosity at which the permeability of the ice becomes non-zero. And so because the water is less dense than the high pressure ice, the water is going to help the ice to move upward, and it will enhance convection and the transfer of heat. So you can see some models, I didn't put it here, but you can see people who say, well, we have heat, we have ice, so we can have a layer of water at the interface between the ice and the rock. The numerical simulations and the physics tell us it's not possible. Okay, so this is the end for the Jovian system. I think I went through some of the major things I wanted to say here. I think some things that we are still missing is this chemical energy here. I think everything else you can find it at Europa in particular, but chemical energy here is really something that we are missing. Okay, let's go to the Saturn system, and I will just speak about Enceladus and Titan. So as I said at the beginning, a factor 10 in radius between the two. Eccentricity, very interesting. So Enceladus has a resonance, so you have a very small eccentricity of 0.5%. But on Titan, you have a very large eccentricity here, and there is no resonance. So it's still a mystery here. Why Titan has such a large eccentricity of 2.9%? When there is no other body here, it can be in resonance. What it tells us is that if there is a lot of tidal dissipation in Titan, then the eccentricity should go down and the orbit should be circular. So it means that there is not much tidal dissipation in Titan. Enceladus, so the surprise of Cassini. This is the south pole of Enceladus, and the camera was able to take pictures of these geysers coming out of the south pole of Enceladus. Actually, the first detection was made by the magnetometer because it creates some kind of plasma. And actually what comes out of Enceladus populates the E-ring around Saturn. So you can see Enceladus here, and you can see the earring around Saturn. So we know that the geysers actually are populating this earring, and by analyzing the earring, we found that there are nanoparticles of silica, so very small particles of quartz, if you want, I mean SiO2, into Enceladus. And so this silica is coming out, and that's why people think that actually it's coming out from the ocean. It's not possible to measure an induced magnetic field in the Saturn system because the dipole is aligned with the spin axis, so there is no variations of the magnetic field around Saturn. Geysers were discovered, and then actually, when we found the geysers, we thought that there was only a pocket of water on the South Pole. We didn't think that there was a global ocean on Enceladus. But by measuring the location of points on Enceladus surface, we were able to determine that there are librations of Enceladus, and the librations are due to the decoupling between the outer ice layer and the inner core. I mean, if there were no decoupling, we couldn't have found such large values for the librations. So you can see here the South Pole, you can see the tiger stripes. There are 4 faults on the South Pole, and the geysers are coming out from this South Pole. So this is a high-resolution image of one of this fracture zone. It's about 100 kilometers long. This is about 2 kilometers wide. It's 500 meters deep. And an idea would be to try to bring something into this fault in order to go to the ocean and to analyze the ocean. You can same thing, very low density of impact craters on the surface of Enceladus. Another instrument, CIRS, so it's a thermal infrared spectrometer, was able to take images, values on the South Pole, and there is very good correlation between the heat that comes out and the location of these tiger faults. So from this information, we know the temperature, and no surprise, the temperature is very close to the melting temperature of ice, so we are very close to 270 Kelvin. So there is a lot of heat inside Enceladus. So this is a kind of cartoon which was published by Caroline Porco in 2014, a global ocean. From the moment of inertia, we need to have either porosity or very low density for the silicates. And by the way, we were also able to determine the thickness of the ice just by having the amount of heat which comes out. Just the equation I showed you before, the heat flux is related to the temperature difference. We know the temperature difference. It's the melting temperature at the bottom. It's the surface temperature at the top. So you have on the order of 200 degrees difference. And so by knowing the heat flux and the thermal conductivity of ice, you get an idea of the thickness of the ice. Okay, this is another view of Enceladus. Okay, but because of the geysers and because there was a mass spectrometer on board Cassini, people were able to analyze the drops, the ocean drops that were coming out. And from these measurements, so you can see here, you find potassium, calcium, magnesium, sodium. You have different elements that were found. And looking at this silica solubility, so remember, actually we didn't find silica in the drops, in the ice drops. We just found them in the earring. It was not the mass spec that analyzed the silica. It was another instrument caps. And by doing some lab experiments, they were able to determine the pH of the ocean. And there were a few papers by Japanese colleagues, Sekine, and also German colleagues, Frank Posberg. So you have some idea about the composition of the ocean, and of course people were interested in knowing whether you can have this kind of situation at Enceladus. I just put here the phase diagram of water. It's not very nice, but here you have the triple point. So you have gas, ice, and liquid. So you can see the liquid is in this domain. And if you look at Enceladus, the thermal profile goes into the liquid, but barely goes beyond the critical pressure. On Earth, actually the pressure is much larger. Remember, the gravity acceleration on Enceladus is 100th time the gravity acceleration on Earth because of the size. So the pressure does not increase very quickly with depth. And so there is a major difference in terms of how an hydrothermal system can work. So the phase diagram is here for the ice. This is a log scale on this side. And for Europa, that's the green plot. And you can see that for Europa, you are much closer to conditions that are very similar to what exists on Earth. Okay, so another paper by Gaël Choblet, we are trying to find out, I mean, it was a big mystery, how you get so much heat coming out of Enceladus, such a small body here. And well, one solution, it may not be the only one, but one solution is that the interior of Enceladus is very porous. So you have some kind of sedimentary rocks, very porous rocks, and they have an effective viscosity which can produce a lot of tidal dissipation. So again, tidal dissipation is the answer for the amount of heat which is produced inside Enceladus. And so in his paper, Gaël Choblet was able to model the temperature of the water and the amount of heat that comes out of the rocks. And so they predict, that there are places where we could have a lot of heat coming out. And so some cartoon came out, from these different studies, where you have Enceladus, the tiger stripes at the surface, a lot of heat produced in the core, and some kind of hydrothermal system. But again, we don't have any. Well, we have more information than for Europa because, of course, we have all these geysers coming out. So we have the composition of the ocean. But what is difficult is to find a chemical energy, so a difference in redox or in pH between the ocean and the porous rock. Because if the rock is porous, then you should get equilibrium between the ocean, the liquids in the ocean and the liquids in the rock. Other information that we got from these geysers is that there is also dihydrogen and methane coming out. And so there was a study by Antonin Affolter and co-authors. They looked at the flux of methane, the flux of dihydrogen, and the ratio between the two. And they developed models where the hydrogen and the methane is produced by either biological activity or non-biological activity. And the conclusion of their paper is, from what we know on Earth for the production of hydrogen and methane, the model where the methane is produced by biological activity is more probable than the other model. But it's just based on what we know on Earth. So I think I'm not, again, it's not my expertise, and it's quite interesting. But of course, it raises the question of, oops, sorry, I'm going too fast, of life on Enceladus, and this ratio. And something I forgot to mention, but I should say that here. Yeah, it's written here. H2 is very difficult to measure. You have to be very cautious about the flux of H2 that has been published in the literature, because when you have particles eating the chamber of the mass spec, then it's going to produce also some H2. So they calibrated. I mean, the team has been a fantastic work of calibrating the instrument. So they are very confident in these values, but I think it was still a challenge. They were not supposed to measure H2 with this instrument. Let's go to Titan. I like this image. So Titan is great, so that's why it's my last satellite, because I can speak hours about Titan, so you will stop me. Titan is great because actually it has an atmosphere. That's the only moon in the solar system with a dense atmosphere. The pressure at the surface is 1.5 bar, but the density is about 5 times the density of the Earth's atmosphere at the surface, just because it's so cold that the density is much larger. So if you compare Titan, you can compare Titan with the Earth, with Venus, with Mars in terms of atmospheric density at the surface. And you can also compare Titan with other icy bodies. I just put 2 of them, Callisto and Ganymede, just increasing the size of those bodies. So Titan is a planet by itself. So here I put a summary of some of the characteristics between the Earth, Io, Titan, and Enceladus. In terms of density, actually the difference between the Earth and Io is mainly due to pressure, because we have much higher pressure inside the Earth. So if I was using the uncompressed density of the Earth, I would find a number which is much closer to that number here. I think it's 3,700 and not 3,500. I want to point out, because every time I show that, I'm just amazed by the amount of heat which is coming out of Io. Out of Earth, you have 42 terawatt coming out. It's a flux of about 100 milliwatt per square meters. Half of that is just the cooling rate of the Earth. The other half is radioactive heating. On Io, just by tidal dissipation, you get 80 terawatt with a flux of 2 watt per square meters. So you have much more tidal dissipation. And when I see the exoplanets we are talking about, TRAPPIST, for example, in terms of the heat which is produced, it's just huge. And I have some ideas, but I think it makes sense to look much more at Io in terms of the comparison with some of the exoplanets. Now, if you look at Titan, I told you that there is, it must be a small amount of tidal dissipation, and you can see that now we are not talking about terawatt, but gigawatts. So terawatt is 10 to the 12th, gigawatt is 10 to the 9th. And in terms of info on Enceladus, 6 gigawatts, so you could say, well, that's not a lot, but because you have a factor 10 difference, it's a factor 1,000 in terms of mass, and so we should have something which would be 1,000 times less than what we have for Titan, and we have obviously much more, and we have heat flux which are on the order of 1 watt per square meters. So these are just comparison between the different bodies in the solar system. Against landing, I will skip that. We can look at it later. So this is Titan before the Cassini mission. We knew that there was we knew that there was methane in the atmosphere, and methane was reacting with, was photolyzed and reacting with dinitrogen and formed some kind of tholins, haze of Titan, and some kind of greenhouse effect, because the surface temperature would be 70 K if there was no atmosphere. So you can see a difference of 20 K due just to the presence of an atmosphere. But we didn't know anything about the surface of Titan. And actually, in order to explain the methane, because methane is photo-dissociated very quickly in terms of geological times, it should disappear in about 30 million years here. So we thought that the surface of Titan would be liquid with hydrocarbons, methane and ethane liquids at the surface of Titan. And what we discovered actually before Cassini arrived at Titan is that it was not the case, because we had some other images. But if you look at some of the radar images, so this is radar images of the northern pole of Titan. I just put the atmosphere with Photoshop or something like this, just to show it's the orange glow has nothing to do with the radar image. But the radar image showed this, this lake. This is Ligeia Mare. And you can see rivers here, which go into Ligeia Mare. So you have flows. And actually, using the radar, the group in Italy, led by Giuseppe Mastro, were able to determine the thickness of the lake. They had a second echo from the bottom of the lake, and so they were able to determine that the thickness of the hydrocarbons is on the order of 150 meters in this area. So you can now, we know the volume of methane that we have in these lakes on Titan. And just looking at how the signal is transferred, the loss tangent, its characteristics of the medium, they were able to determine that it's about 2/3 methane, 1/3 ethane. So it's just amazing what you can do, something which was not foreseen, when we built the Cassini mission and the radar, but this information became available. So on Titan's surface, not only were we able to see the dunes with the radar images, you can see the dune fields. The sand is made of organic material which is produced in Titan's atmosphere, but in the infrared we found out that there are several atmospheric windows where we can see through Titan's atmosphere, and so we can see the surface also in the infrared. And this is an image that I like. It's a specular reflection on the northern lakes on Titan that we took at 5 micron, where there is very little scattering. The Huygens probe landed in this area. Actually, you can see here images that were taken by the probe when it was landing on Titan. And then from orbit in the infrared, we were able to get the same kind of morphology that you can see here. And so we got the spectra also on this area. I'm just showing that because here you have the dunes around, and the next mission that will be sent to Titan it's a drone, Dragonfly, and it's going to land in this area. And the idea is to explore this impact crater, which is named Cell Crater, which is located here. And this is a view, the first view of the landing site that we had, and I know that some people thought that it was a view of Mars when they saw that. But when you look at the spectra, it's clear that it's ice covered with some kind of organic material. Very few impact craters on Titan. Here is the largest one, Mernva crater, 400 kilometers in diameter. Here you have Synlab crater, which I think it's 25 kilometers in diameter here. And with infrared, we have some infrared information. Actually, this one is pretty well preserved, which means that it must be pretty young. And this one is so big that models predict that it was able to go through the ice crust of Titan and to bring material, to transfer material from the surface into the interior. We have maps of the clouds on Titan. So this is a fraction of clouds as a function of time and latitude. So here you have the latitude, longitude, and the colors tells you what the fraction of time you have clouds on Titan. So this is winter, and you have ethane clouds on the high latitudes, northern latitudes, and then you have some methane clouds between 30 and 60 degrees south during the winter. Also, you can see it's clear sky at the equator, very little clouds. We observe some, but not very often. Actually, at the equinox, we observe some clouds. One question that is not really resolved, although here is an answer, is ethane. Because as I told you, methane is photodissociated and will produce mainly ethane. but there is almost no ethane in Titan's atmosphere. So one idea is that actually when it rains ethane on Titan, ethane is going to be trapped in ice, and we know that it can form what we call ethane clathrates. So actually I told you that ice is kind of very porous at microscale, and actually you can put molecules like methane, CO2, ethane, a number of particles or molecules, in the crystals, and they form what we call the clathrates. It's important because clathrates has very different properties than ice in terms of heat transfer. You can do, global scale distribution of methane on Titan. So we have numbers in terms of mass of ethane in the atmosphere, the mass of methane and ethane in the lakes, in the dune fields also, what is produced in the upper atmosphere in terms of ethane, and the fact that ethane should be trapped in the subsurface, and then you have the formation of these ice particles. So this slide is kind of old, so I think there may be some updated numbers for these values. Okay, and so one question is about methane in the atmosphere, and is there any cryovolcanoes that would release methane in the atmosphere? It's possible actually that when you have impact craters, if you have these clathrates, methane clathrates or ethane clathrates, then you can destabilize the clathrates and then you can get some methane released into the atmosphere. And this is a model that we developed with Gabriel Toby and Jonathan Renin about the evolution of Titan. I want just to point out that at the beginning of Titan's geological evolution, actually we predict that the ocean would be in contact with the atmosphere, that there would be no crust on Titan. And then it's very speculative about the more recent time where the crust would be thicker, but we don't have any measurement of the thickness of the crust except by impact craters, because they give us some lower limit for the thickness of the ice crust. I won't speak about those. Just want to show this cartoon. It's a difference between Titan and Ganymede. Although they have about the same radius, the gravity acceleration is a little bit lower on Titan than it is on Ganymede. And if you plot this is H2O phase diagram, so you already saw it, the low pressure ice, then the high pressure ices, and depending on the thickness of the ice crust, it's quite possible. So if it's very thin, 50 kilometers, when you do a adiabatic profile in the ocean, what you find out is that the ocean is in contact with a silicate core. So early on, when the thickness of the ice crust was small, then the ocean was in contact with the silicate core on Titan. And then when it cools down, then the temperature decreases, and you can see that you cross the freezing point of water in ice 6, one of the high pressure ice. And if it's even colder, then it starts in ice 5 and eventually even in ice 3. But we don't know what the thickness of the ocean, and you can, I forgot to tell you, how do we know that there is an ocean on Titan? Because I told you it cannot be the magnetic field. So what kind of measurements do we have? Yes?
The density?
The?
Density?
So the density, no, because it's non-unique, so it cannot be just the density here. But related to the density distribution is K2 love number. We have a very large value of K2, which is possible only if you have a liquid layer in between the outer layer and the interior. So it's again a gravity measurement that tells you that there is, well, actually the K2 number, which has not been measured for Ganymede and Europa. It has been measured for Titan because we had many more flybys, so we were able to get this value of K2, and also Titan has an eccentricity of 2.9%, which makes this measurement much easier. So the K2 number, and also Titan has a very small obliquity, and it's very hard to explain the obliquity if you don't have a decoupling between the outer ice layer and the interior. So we have two observations. 10 years ago, there was a third observation which was made by Huygens, and it was an electric field, what is called the Schumann resonance that we know on Earth. When you have storms, thunderstorms, then you have electric field in the Earth, and you have the electric fields that can trigger, and it's going to bounce between layers. And they thought that they had the same kind of signal when they landed on Titan with a Huygens probe. But they did some tests with a similar probe at ESA, and they found out that it was not possible to explain the measurements by this kind of resonance. So it's only two: gravity, K2 number, so the way Titan deforms during its orbit around Saturn, and also the obliquity. Okay, so next mission to Titan is Dragonfly. It's very interesting, you know, because the New Frontiers program at NASA, it's, okay, I think that will work. The New Frontiers program at NASA was defined 12 years ago in terms of what are the targets for this program. And there were 6 targets. And none of those targets were in ocean worlds. And because of the Cassini discoveries, they added, for the last call, they added Titan and Enceladus. And sure enough, they didn't pick Venus, they didn't pick the Moon, they didn't pick, I can't remember what was the others. They chose a mission to Titan. So that's how we got a mission to Titan in the late 20s. It will arrive at Titan in the mid-30s. And the idea is to send a drone, so it will be able to land on Titan and then to move different places on Titan. Quite a challenge to send a drone on Titan, but Titan is a good planet where you want to fly. You don't need big wings because the density is so large that it's pretty easy to fly. So to summarize, in terms of ocean worlds, of course we have the Earth. We're talking about environments where life could have emerged, and oceans or interface between ocean and rocks are considered as possible environments. I told you that we have that kind of environment on Europa. We have that kind of environment on Enceladus. We may have had that kind of environment on Titan early on. Difficult to say the same thing for Ganymede and for Callisto, but you know, all these bodies, Triton also is thought to have an ocean. I can answer questions if you have questions about Triton's ocean. But anyway, so these 4 bodies, Enceladus, Europa, Titan, and Ganymede, are 4 bodies with very high interest in the community. Europa Clipper is going to go to Europa. It's going to be launched in 2024. I told you JUICE will be launched, and the main target is Ganymede. Also, JUICE will do also some flybys of Europa, and quite a lot of flybys of Callisto, which will be quite interesting because we know very little about Callisto. So that will be the future of this world, and we can dream even further, and we can think that at some point we will be able to sample Enceladus ocean and maybe bring back some of those samples to Earth, because I think that if you want to do very fine characterization, it's much easier to do on Earth than it is to do in situ. And then you can, depending on the thickness of Europa's crust, you can imagine that you can drill through the crust and also access the ocean. So that's, I think, what I wanted to tell you about ocean worlds and why we explore them. Thank you.